All right, so this is right after going over all of these with shapes and VSEPR theory. And again, I think whatever the quote was at the beginning of these slides was something like, no theory is able to catch everything. So VSEPR theory is good for predicting practically what the shapes of molecules are going to be. It's very quick. It's pretty easy to do compared to other things. But it also is somewhat incomplete and is definitely an oversimplification. So more advanced bonding theories take quantum mechanics, which of course is very complicated and requires a lot of math, which is why Lewis theory is so easy and quick. But it applies the quantum mechanics and then predicts how different valence electrons form bonds. And you can calculate all kinds of different properties like bond length, strength, molecular geometries, dipole moments. We're not going to be doing that math. We're just going to be taking like an overview look at it to see, in theory, this is how the quantum mechanics comes together. We're not going to actually calculate anything because, yeah, quantum physics. Which, yeah. I should ask my cousin about this sometime, but every time I ask him about theoretical physics, yeah, my cousin has a PhD in theoretical physics, and it's every time he tries to talk about anything, it's just completely unrelatable. So we put the mask on and we just talk about weird rules and exceptions, because that's better than the alternative. So valence bond theory treats these bonds as orbital overlaps. So electrons, we saw they reside in quantum mechanical orbitals localized on individual atoms. So it's talking about just the atom. So if I have one atom not forming a bond, it's got all these different quantum mechanical orbitals, these different fun shapes. You got S, P, D, and F atomic orbitals. But those orbitals can be hybridized. And when you bring together two or more atomic orbitals, especially as two atoms approach each other and a bond forms, it's favorable most of the time for those orbitals to actually change shape, merge together, and we get different waveforms out of the quantum mechanics predicted. So you get different shapes to those orbitals. And for our overview, we're just going to say it's these two orbitals or these three orbitals or these several orbitals that are just blended together to get a new shape. And of course, the goal is always to lower the energy through the interaction. So that new orbital doesn't exist in the atomic, like with one atom, because it's higher energy than if you just had the hybrid orbitals in the molecule. So always going for lower energy. So simplified diagram of the potential energy between two hydrogen atoms. Oh, actually, there's a fun simulation of this on PhET. Let's see, where is that? I missed it. I know I missed it. Oh, here we go. Atomic interactions. So yeah, these atomic interactions. And so I can take this atom and I can push it closer. Let's see, can I change? Let's do custom attraction. There we go. Just gonna emphasize this. So if I grab one of the atoms and I let it slide, it'll drop down into that energy sink, and then it comes back out, and then it drops back into the energy sink, and eventually it ends up just getting stuck in there. So it's going to take a while, but it'll go in and out and in and out. And the optimal distance for those two nuclei is right at the lowest point of that curve. Now I can't grab it and make it stop. All right, I guess it's going forever. Got to be quicker than that. So the best orbital overlap is basically the compromise between the electrons repelling each other, the nuclei repelling each other, and the overlapping orbitals, creating better energy states for those electrons. So if you get too close, you start getting the nuclei repelling each other. If you're too far away, then you don't have good sort of coupling of those electrons to form a bond. And so there is some minimum, that's the ideal distance.
So this is like during we're doing that loose star structures. That's why there's like bonds together.
Yeah, this is like yeah, basically. So the bonds that are forming are going to be at about this minimum distance. Of course, they're never just sitting still. They're always like moving and vibrating. Both. So this is not the electron. This is the, if it was two hydrogen atoms, they're two hydrogen nuclei coming closer together. And then as their orbitals overlap, they minimize energy up to a certain point, and then the nuclei get too close, and then that potential energy spikes. And so then they try to get farther apart. And so they'll settle into some ideal distance. You want to be close, but not too close.
So does the nucleus have a higher?
It's all based on distance. So it's because it's Coulomb's law. So it's like the Q1, Q2 over, I think it was R squared. But it's related to the distance too. So that repulsive force of the two nuclei is going to get stronger the closer you get, but it gets weaker the farther you get. So it's not necessarily that it's overall just stronger. It's just that there's some point where it gets to be too much, and then there's a distance too far away also. That's hard to describe.
Possible for hydrogen to just break off.
Like spontaneously?
Just keep going back to that curve. Is it possible that potentially just
There'd have to be something to make that happen. Possibly. Table this for later. Let's put a pin in it. You got to get through more slides. So the interaction energy is usually negative, meaning it's stabilizing. So just like with the electrons, where we saw the electron away from the nucleus, we said that that was 0, and as it gets closer to the nucleus, that becomes a larger and larger negative energy. So same thing here, where as they get closer, that potential energy, or the interaction energy, is negative. So we're getting into a lower energy state than the two things separated. So commonly, the electrons come from two half-filled orbitals. So we've got one orbital on one atom. So really easy with hydrogens, because the hydrogens only have one electron each. So when they come together, they're each sharing one electron from their half-filled 1s orbital. And then when those orbitals overlap, it creates a hybrid orbital between the two, and those electrons get to have opposite spins. So the valence electrons in a molecule, they reside in quantum mechanical orbitals when we just have for the molecule and for the atom. The shapes of those orbitals change as they come together. And then there's some optimal amount of overlap and combining of their two orbitals that gives them a most minimum energy. And then whatever orbitals are overlapping and whatever the shape is, that's whichever orbitals are overlapping determines the shape. And then we've got some molecules that, according to VSEPR theory, don't get predicted very well. So like this one, so the actual bond angle for this, what is this? This is H2S. So if we did a Lewis structure, we'd get something like this. Oh, that's an S, that should be an H. All right, so you'd predict probably, because it's got 4 electron groups, the electron geometry would be tetrahedral. And then the molecular geometry would be bent. And we'd have angles of 109.5 degrees, approximately, right? It'd be less than that because we've got lone pairs. But the actual molecule has angles closer to 90 degrees. So you go and measure it, and it's, oh, that fell apart. And it's not just because of the stronger, like that these lone pairs are somehow stronger and it's pushing the hydrogens even closer together. But when the hydrogens interacting with the sulfur, what's happening instead is each of the hydrogens has one half-filled orbital, and the sulfur has 2 half-filled orbitals. And they're p orbitals. So remember, the p orbitals are these red dumbbell ones. And so by overlapping with 2 of those, there's no hybridization taking place here. So like it's not combining any orbitals. So the hydrogens line up with the existing p orbitals on the sulfur. So it gives you pretty close to 90 degrees, since that's the angle between those p orbitals. So what is a chemical bond? What is it according to Valence Bond Theory? E. VSEPR or Lewis theory would say D, that it's a shared pair of electrons between two atoms. In valence bond theory, we say it's a half-filled atomic orbitals on two atoms. So if you had a hydrogen which has a 1s with one electron and another hydrogen, the 1s, and it has, I'm just going to draw it with the opposite spin, one electron, those two orbitals come together to form a bond. Okay, so carbon, if we're like, again, we just looked at H2S, hydrogen sulfide. The H2S, sulfur had its 3s was filled, and then its 3p. It had 1, 2, 3, 4. So it had two half-filled orbitals. So when hydrogen forms a bond with sulfur, we saw that it had angles of 90 degrees. And again, if we're thinking like half-filled orbitals for something like carbon, right? So carbon has, oh, I need to turn that filter off. It's making that look weird. Okay. Carbon has two half-filled orbitals. So according to valence bond theory, at least so far, we might expect, hold on, I'm going to turn this filter off. That should look a little bit better. Yeah, now it's not like twitching and weird on the hydrogens. So, right, so we might expect, okay, I can only add two hydrogens then. So we've seen CH4, it exists. It's got angles of 109.5, so it's not this 90 degree it's predicted here. So I've mentioned it already, but what happens is you get hybridization. So hybridization is actually the mathematical procedure in which you take the standard atomic orbitals and you morph them into and combine them into hybrid orbitals. So the shapes and the energies of the orbitals change. And this better predicts the shapes of molecules when using valence bond theory. But I really just want to show you the picture of what this looks like first, and then we can come back to these other points. So when we take carbon, right, we know the 2s orbital is lower than the 2p orbital in energy. So that's why the 2s fills first, and we fill those in with two electrons, opposite spins, and then two get to be split out in the 2p orbital. But what happens when you hybridize the orbitals is now it takes the 2s and the 2p orbitals, and it merges them all together, and you get orbitals that are a little bit of both. And it also makes all of the orbitals the same energy, which we would say that the four hybrid orbitals are degenerate, just meaning they have the same energy. So now if we bring hydrogen in, if we bring hydrogen in to bond with this, we've got our half-filled orbitals. So now each of these half-filled orbitals can bond with a hydrogen. And that's how we get the four hydrogens. And the geometry of these sp3 orbitals is tetrahedral. And that's something that just, again, comes out of the math. But again, why? Why form these hybrid orbitals? When you take the orbitals and you hybridize them, again, you're taking properties of both. So the s orbital is just a sphere. The p orbital is this dumbbell shape. But the whole thing that gives like the optimal distances when these bonds form is how much the orbital of the carbon can overlap with the orbital of one of the hydrogens. Now the hydrogens, they're just s orbitals, so they don't really do anything to extend the reach of their orbital. But when you blend the s orbital and multiple p orbitals together, you see the shape changes a lot. So the orbital gets longer on one side, and it becomes really short and stubby on the other side. So that means that the carbon's orbital is actually able to reach out farther and overlap better with the hydrogen. So it's like kind of the two things go hand in hand, that we want to maximize orbital overlap. And by doing this, it does bring the energy of the 2s orbital up. So it does make that orbital sort of higher energy, but it also makes the energy of the 2p orbitals lower. And then because we get better overlap between all of these orbitals and the hydrogens, then you get an additional benefit, additional energy benefit from that.
So does this
No, this happens with anything in theory. So the hydrogen itself is not hybridizing because it only has one orbital, but the carbon is. And so the hybrid orbitals minimize the energy by maximizing the orbital overlap in the bond. And as I pointed out, the electron probability density gets more concentrated on one side than the other. One lobe becomes much larger, the other lobe becomes much smaller. So that electron is actually spending more time on the side with the bond. And again, we're just looking at these as simplified a little bit. So just assuming that the center atom hybridizes. And so that's why, like on that worksheet, right, you can basically just, however many bonding or electron groups there are, that's how you figure out how hybridized it is. Okay, so again, these orbitals go from being evenly distributed on either side. Maybe it's easier to see with the PZ. Evenly distributed, then we end up with an orbital that ends up mostly on one side. And ends up being a tetrahedral. So that's the sp3 hybridization, and it's called sp3 because it's using one s orbital and three p orbitals. So you just add them up. These can also contain just lone pairs of electrons. So NH3 is that trigonal pyramidal. And one of those hybridized orbitals, still hybridized, but it's a lone pair instead of having a bond. So how many sp3 hybrid orbitals, so how many total orbitals do you get when you mix one s orbital and three p orbitals? 4. So the total number of orbitals doesn't change. We just remix them.
It's like 1s and then plus the 3s, or the 3p.
Yeah, so 1s plus 3 of the p orbitals. And that gives you the sp3. Now, sp2 hybridization is usually when we have a double bond. So in the case of a double bond, we only take 3 orbitals and we mix them together and we get the sp2. So 1s and 2p orbitals. And then that last unhybridized p orbital gets used for forming a double bond, or as we'll see in a second, a pi bond. That's what it's called. So similar kind of thing that happens is that we get the s orbital, we get the p orbitals. But now instead of having the tetrahedral, the hybrid orbitals are all in the same plane, and they're trigonal planar. And that means that the last p orbital that doesn't get incorporated here, can't see it there, can go above and below. Try and do it like this. So we got 1 p orbital, 2 p orbital, 3 p orbitals, and then or sp orbitals. So this would be an unhybridized p orbital. These ones would be the trigonal planar sp2. So H2CO, formaldehyde, has sp2 hybrid orbitals. So the carbon can form 4 total bonds. Two of them get formed with, and then, yeah, 2 with the oxygen. One is a single bond and the other is the double bond. There's the double bond being 2. So in order to form a second bond with the oxygen, because the oxygen's got 2 unhybridized orbitals, hydrogen again only has 1. So the hydrogens would occupy 2 of these, and then 1 p orbital would be one of the sp2s, and then the other oxygen's other electron forms a bond with the p orbital. And you get something crazy like this. It's called a flower diagram. So you gotta see, there's this plane, so there's like a table here, imagine like a clear glass table. The red here on top and bottom is the p orbital that forms this side-to-side overlap, side-to-side bond. And then the sp2 orbitals are all in the plane of this table. So they're all cut in half by the table. One sp2 orbital sticks out towards the oxygen, And then the other two stick out towards the hydrogens. And even on here we have it labeled. So these are labeled as sigma bonds. And then this one is the pi bond. I think the sigma bonds make sense. It's sticking out in that direction, right? Single bonds, they're overlapping because they're sticking out in the same direction. The way that p orbitals overlap is a little bit weird because they do this thing like side to side thing. And it doesn't feel like that maybe they should overlap, but they do. And so that electron is being shared above and below the plane of the other bonds. You got your pi bond and your sigma bond. I think the pi bond kind of even looks like a pi bond. So then the notation used to mark these, what type each bond is, you say like these right here, the sigma bonds, we have carbon using an sp2 orbital to form a bond with hydrogen's s orbital. So this is saying carbon's sp2 orbital is forming a sigma bond. I guess I could just use this symbol with hydrogens s orbital. Should be pretty obvious why we use shorthand notation for that. Whole long sentence. All right, so that's all that means. I have carbon using an sp3 orbital, making a sigma bond, hydrogen, and hydrogen's s orbital. And then for the oxygen, again, we're assuming that, like, we're focusing on one atom here, and then the other ones we're just going to say they stay unhybridized. But the oxygen here is using a p orbital, and again, it's another sigma bond with carbon's sp2. And then the pi bond is between p orbitals on the carbon and the oxygen. These things they end up being a mess when you try to draw them out by hand. Yeah. Yeah, it's basically just saying that there's a bond between the two, like this dash. Yeah. Double bond, yeah. One of the bonds is a sigma bond, the other bond is a pi bond.
So then the pi and the sigma bond make a double bond?
Yeah.
So then if one of them was taken out, then it just like
a single bond. Yeah, the pi bond would be the one that would, I guess, break first. If you can think about them breaking first. I always think of, actually, I just reminded of this. I always think of the pi bonds, or like double bonds, as being like when Dragon Ball Z, when Gohan and Trunks do their like combination thing and they combine, that's the pi bond.
The top and
Oh, now I
Oh.
can see that.
Yeah, right?
top and bottom piece, that's just one bond, right? That's just representing the one bond. The one.
Yes. Yeah, so this thing on the top and the bottom is the one pi bond. And the electrons are written up here as being upspin, downspin, but they'd be anywhere in that whole region.
wait, so the pi bond is to both top and the bottom?
Top and the bottom is one pi bond. So that's why you did this.
So then that middle part shared electrons.
Yeah,
Where that thing is pointing, that's that sigma bond,
this is the sigma bond,
and then those.
pi bond,
Okay, so those two things are just one pi bond.
one pi bond.
One. Okay.
Nope, one pi bond, one pi bond. But what if two pi bond? Look at that. So double bond in the Lewis model always corresponds to one pi, one sigma bond. Or in valence bond theory. So we're just like, that's always what it's made up of. And in reality, that's pretty much what it is. In general, the pi bonds are weaker because they have worse overlap. So it's less efficient, it's less effective than that end-to-end overlap with the sigma bonds. So they're generally easier to break, more reactive. So if you remember this, I don't know, years from now, if you take OChem, the pi bonds are easier to break. Oh, so the other thing that happens when you form this pi bond, because it's connected over the top and underneath, it prevents rotation. So they're coupled. If this was to rotate, that would get these p orbitals out of phase. And so there'd be a huge increase in energy. Basically, you have to break that bond in order for this to rotate.
They can't like rotate together.
The whole thing can spin,
Okay.
but it can't rotate. One side can't rotate relative to the other side. Whereas the sigma bonds are free to rotate because that does not affect how much they overlap. Oh, so then a molecule like this, where you have the chlorines on the same side versus the chlorines on opposite side. So it's cis, meaning the same side, or trans, 1,2-dichloroethane, or ethene, putting the chlorines on other sides. So these would be like distinct molecules. They'd have different properties. There's a whole wall of text. So double bonds, shorter, stronger. According to Valence Bond Theory, why is a double bond not simply twice as strong? Oh, okay. Why is a double... Wow, that's...
Damn, you could really simplify that.
It could really just be this. Why isn't a double bond twice as strong? There's a sigma bond. That's basically a sigma bond and a pi bond. That's the same strength. But then the pi bond is that stronger or weaker than the sigma bond? Weaker. Because they're just side-to-side overlap.
Double bond can never be two sigmas.
Double bond can never be two sigmas.
Why not?
Because then they'd be occupying the same space.
That makes sense.
All right, so yeah, because according to Valence Bond Theory, two different kinds of bonds, sigma and a pi, and the pi bond is weaker than a sigma bond. Like I said, what if two pi bonds? So triple bonds are when you have just a 2s and a 2p, or really just an s and a p orbital that hybridize, that leaves two unhybridized p orbitals. So this would be sp hybridization. Again, count the number of electron groups, because a triple bond would count as one electron group. So those unhybridized p orbitals can go off and they can form two pi bonds. And again, we get very similar shapes for the sp hybrid orbitals. Together, they look like a single p orbital, but in reality, they're just overlapping in opposite directions. And again, this is all, I guess, in valence bond theory, it's all about having half-filled orbitals. So carbon hybridizes two of those. It gets the s and p orbitals, or the sp hybrid orbitals, and then two leftover p orbitals, meaning 4 total bond opportunities.
So is it always gonna have like 4 boxes?
Yeah. Basically, carbon always wants to form 4 bonds because carbon can hybridize in a whole bunch of different ways to have 4 half-filled orbitals. Actually, if I do this with like oxygen, so if we take, or nitrogen. So nitrogen would be the 2s, and then we have 1, 2, 3, 2p, so this would be 1, 2, 3, 4, and 5. So for nitrogen, how many bonds do you think nitrogen wants to form? How many half-filled orbitals?
3. Ah, I know.
3. So nitrogen pretty much always wants to have 3 bonds, whether that's 3 separate single bonds or double bonds or triple bond, it'll form 3 bonds. So triple bond, even harder to see in a flower diagram what's going on. But now I've got 1 pi bond on top and bottom, and then another pi bond on the front and on the back, forming that cross coupling. So do you think triple bonds can rotate?
Nah. Oh, nah.
Harder or easier to rotate than a double bond?
Harder.
Harder, right? There's now 2 directions or 2 pi bonds that are restricting its rotation.
So by rotation, you mean like the center part to rotate?
Yes, if I held this side still and then tried to rotate this side, does not rotate.
But it would all rotate as one.
Yeah, the whole thing's going to be spinning and tumbling and flexing, and
Sigma.
yeah, only the sigma bonds on the end would be able to move. All right, so what about hybridization of carbon and CO2? Really, the best way to do this is to draw out a Lewis structure. So how many electron groups does the carbon have?
Electron groups.
Electron groups. Same as like the VXE theory or notation. So it's just 2. So carbon then is forming at least a sigma bond. So it'd be like so one of these carbon-oxygen bonds would be sigma. And this other one would be a sigma bond. So that's 2 single bonds. And then the double bond would make it a pi bond each. So because we only have 2 electron groups, then we're only hybridizing 2.
Is that like a notation where you write the sigma and pi on each bond?
No, just made that up. Yep.
But then you actually do it.
That's his thesis. Proposing a thesis.
So we're, oh man, we got to talk about. All right, we can speed through those real quick. But if we look at just, again, we're half-filled orbitals. So to form carbon, so this is a 2s, and then we've got 2p, there's 1, 2, 3, 4 for carbon. And the carbon's going to form 2 bonds with each of the oxygens. And so to form a double bond, again, the double bond's always going to be a sigma bond and a pi bond. And to have a pi bond, we have to have half-filled p orbitals. So if I take 2 of these orbitals and I hybridize them to make the sp, then I can put 2 electrons in there, and then I have the 2 p orbitals, which each get 1 electron each. So these become the 2 pi bonds, these become the 2 sigma bonds. And so basically for every step up from there, we're incorporating more and more orbitals. So like d orbitals, sp3d2, these aren't going to happen with, like, carbon's not going to be able to do that. Because at n equals 2, to go back to quantum numbers, carbon would be n equals 2, which means that L can be 0 or it can be 1. It can't be 2, so there's no d orbitals. So this is going to be for basically row 3 and below, all those ones that can do expanded octets. So your trigonal bipyramidal arrangement is sp3d, because we've got 5 orbitals that all get hybridized to form bonds. So that would be like arsenic pentafluoride, which sounds like a horrifying molecule. Super poison, probably. And then for 6, so the octahedral is taking all of the s, all of the p, and then 2 d orbitals to give you the octahedral. So total of 6 bonds. Or lone pairs. You can have lone pairs in there too. Sulfur hexafluoride. Sulfur hexafluoride is not poisonous. If I remember correctly, obviously don't go out and just breathe sulfur hexafluoride on that alone. But it's a super dense gas. So that's the one that people will breathe. It's like helium. If you get a breath of helium and then you talk, your voice is super high pitch. Sulfur hexafluoride does the opposite. It makes your voice super deep.
I die from sulfur hexafluoride.
Huh?
Can you make it?
Can I? Probably not. I don't know. Never tried and haven't thought about it.
Next lab.
Okay. Next lab.
We're gonna make it.
Yeah, so this is why I wasn't super worried about this part, because basically just assign hybridization schemes from the electron geometry of the interior atoms, which basically amounts to how many electron groups are there. That's how many orbitals you incorporate. So I wrote on the board, actually, was it? Yeah, number of electron groups. So 2 electron groups, sp. Take 2 orbitals, you hybridize them. 3 electron groups, sp2. Take 3 orbitals, s, and then 2 p's, hybridize them. 4 is sp3, 5 is sp3d. In terms of like the practical, put something down on the page for how many electron groups there are on the final. That's all you need to know about that. In terms of valence bond theory, you need to know that it's the overlap of orbitals. And I am quite fond of like this, where is it? Like these diagrams, where you show the sp, you show all the hybrid orbitals. Shoot, this is probably the one that I would give you. There's the one with hydrogen. Basically this kind of sums up all of it, that if I want carbon to form 4 bonds that are all equal energy, then we're going to have 4 hybrid orbitals. And so the combination of this 2s orbital going up in energy and then the 2p orbitals coming down in energy to form these 4 degenerate orbitals. That's what I want you to take away from valence bond theory. Half-filled orbitals.
Why do they want to be